All right, so let's get to how we draw Lewis structures. Now, I like to think of this as maybe not the most important thing you'll learn in general chemistry, but it's pretty darn close. And it's something that if you master, it will make your life so much easier in this semester and the next semester, and even into organic chemistry. If you procrastinate or you decide to just push it off and not work on it, it will haunt you all throughout GChem and OChem as well. So before we get to, how to draw them, let me talk about kind of the foundational concept behind it, and that's the octet rule. And I'm going to put rule here in quotes because it really is more of a guideline. Um, the octet rule basically says that atoms can't have more than 8 valence electrons. Now, there are a lot of exceptions to this. Right off the bat, um, hydrogen and helium, okay, hydrogen's, even though I know it's on the left side, hydrogen is a non-metal. Sometimes you might even see it kind of like over here on the periodic table, but hydrogen's a non-metal. Hydrogen and helium are happy with 2 valence electrons. In fact, they can't hold anymore. The only orbital they have is a 1s orbital. So they physically cannot hold anymore. And this no more than 8 valence electrons, it's only true for the second period, the second row. Carbon, nitrogen, oxygen, fluorine, and neon. Now, I do want to back up and say I'm only talking about the non-metals here. Those are the ones that covalently bond. Period 3 elements, or I should say period 3 and below, can have more than 8 if it helps minimize the formal charge. And we'll see some examples of that. So, like phosphorus, sulfur, so on, those period 3 and below elements can accommodate more than 8 valence electrons. So that's why, the octet rule isn't like a hard set rule. It's kind of a guideline that we try to follow so that we can draw the best Lewis structure. So let's get to the steps. I'm going to go through this in 4 steps. First and foremost, kind of consider this rule or step 0. Um, you got to practice. Just like Yoda says there, if you want to master this and make your life easier in all of GChem, you have to practice drawing Lewis structures. And there's multiple resources out there that will give you tons of practice. The textbook, there's problems in the textbook. I'm going to post resources up on Canvas. Um, I'll say this again at the very end. You can always practice drawing your polyatomic ions. Draw the Lewis structures for those. But there's tons of ways to practice this, and that's the only way you are going to master this. So step 1 is count the valence electrons. So however many atoms there are, you add up all the valence electrons for all the atoms, just valence electrons. Now, as a side note, if something is charged, so something has a plus charge, you're going to remove 1 electron from the total. Because something's positively charged, you have to lose something negative, an electron. If something has a negative charge, for every negative charge, you're going to add 1 electron. So you'll notice some of the polyatomic ions are like -2. So in the total count of valence electrons, you would add 2 more. And what I'm going to do is go through all 4 of these steps with the same compounds and just kind of go through the process of how we come to a Lewis structure. So we're going to look at carbon dioxide, We're going to look at ammonium. We're going to look at methanol, and then nitrate, sulfuric acid, and the acetate ion. Okay, so this can be done very quickly. If you know your valence electrons, we got one carbon, so four valence electrons there, and we have two oxygens, so six valence electrons for one oxygen. We're going to multiply that by two, and that's a total of 16 valence electrons for carbon dioxide. With ammonium, there's one nitrogen with five valence electrons. For hydrogen, each hydrogen has one valence electrons, and we're going to multiply that by four because there's four in the formula. And notice that we have a plus charge. So we're going to subtract one electron from our total, and that comes out to 8 valence electrons. All right, with methanol, we have one carbon. There are four hydrogens. Let me back that up a little bit. Hydrogen has one valence electrons and one valence electron. We have four of them. And then one oxygen for six valence electrons. That comes out to a total of 14. So nitrate, there's one nitrogen with five valence electrons. There are three oxygens, each of them with six, and we got a negative charge. That means we got an extra electron to add. So that comes out to 24 valence electrons. So for sulfuric acid, there are two hydrogens, each of them with one valence electron. There's one sulfur with six valence electrons. And there are four oxygens, each of them with six valence electrons. So add all that up, that comes out to 32. And then for acetate, there are two carbons, each of them with four valence electrons. There are three hydrogens with one valence, each with one valence electron, and two oxygens, each with six. And notice that acetate has a negative charge, -1 charge. So we're going to add one electron. All right, so that's the first step. In any problem involving drawing a Lewis structure is find out how many valence electrons are in that compound. Step two, we're going to kind of put together a skeleton. We're not going to draw any bonds. We're not even going to draw any electrons. We're just going to kind of try to not guess, but use some guidelines to help us put the atoms in order. So I'm going to give you a series of guidelines, and this will come with a lot of experience in recognizing these things. So number one, hydrogen is always terminal, meaning it's always at the end. Or sometimes I like to call it an outer atom. We'll have central atoms or center atoms, and then we'll have outer atoms. Hydrogen's always on the outside. If you're trying to decide what to put in the middle, generally the less electronegative atom is in the center. Now, one common motif I want to point out, and as you do more and more, you're going to see more and more common motifs, but one that comes up quite a bit is the OH group. And you'll see that bonded to some sort of atom. Sometimes the formula gives you hints, and we'll see that in some of the examples. Sometimes it tells you what atoms should be bonded to which atoms. And then finally, the last guideline I can give you is don't get super crazy with your shapes. We'll talk about molecular shapes in the next set of lectures. So once you have a handle on that, that fifth guideline kind of becomes a little bit more clear. Okay, so let's do this for our examples. We'll start with CO2. Okay, well, carbon's less electronegative than oxygen. Okay, how do I know that? Well, that's the periodic trend. It's further to the left than oxygen. So all I'm going to do is put carbon in the middle. I'm going to put the oxygens on either side. And with ammonium, I don't really have an option to put, I can't put the hydrogen in the middle. I'm just going to put the nitrogen in the middle, and the hydrogens are going to go around it. Now with methanol, this kind of points out a couple of our guidelines. Number one, the formula is giving us a hint. It's telling us here that these three hydrogens are going to be attached to that carbon, and this hydrogen is going to be attached to that oxygen. So I'm going to put the less electronegative atom in the middle, put some hydrogens around it, and then I'm going to have the oxygen next, and then the hydrogen is going to be bonded to that one, that oxygen. Now with nitrate, nitrogen's less electronegative than oxygen, so it's going to be in the center. And I'm just going to put the oxygens around it. And then let's look at sulfuric acid. So I'm going to put sulfur in the middle. I'm going to put the four oxygens around it. You might ask, well, how do I know I'm supposed to do that? Why don't I attach hydrogens to the sulfur as well? This kind of comes with experience. And plus, it'll become a little bit more clear once we start doing the next step of why I arrange the oxygens like this. And then going off of, again, this kind of common motif, OH shows up quite a bit when you have oxygens and hydrogens. I'm just going to put a hydrogen around two of the oxygens. Doesn't matter which one, I'll just put them here and here. And then let's look at acetate. So again, we got a little bit of a pattern here, where the formula is telling us something that these three hydrogens are probably attached to that carbon. So let's start there. And I'm going to put the carbons in the middle because they're the less electronegative atoms. The hydrogens around here, because that's what the formula tells me. Now I have two options for these oxygens. I can put them both bonded to the carbon, or I can bond one to the carbon and the second oxygen to the first oxygen. Now, over time, again, once you recognize a lot of the templates, you would see that this is not going to lead to a good Lewis structure. And in fact, I'm going to carry that over. I'm going to carry those two structures over to our next rules, or I'm sorry, our next steps, and you'll be able to see why we don't like that second answer. All right, in step three, we're just going to add single bonds and lone pairs. Now, where are we going to get these electrons? We're going to use the valence electrons we added up in step one and start with one bond from each terminal atom to a more central atom. Second part of this is we're going to give atoms lone pairs to complete an octet or complete a valence shell, starting with the more electronegative atoms. Most likely those will be terminal because the less electronegative ones will be in the middle. And along the way, we're going to keep track of our valence electrons because we can't add more electrons than than what we calculated in step one. All right, so let's start with CO2 again. So in CO2, we said they should be arranged like this. Oops, not like that. We don't put the bonds in yet. So that's what we said on the previous page. Now what I'm going to do is put single bonds here. Oh yeah, got 16 valence electrons. When I put those two bonds in, I'm going to take away 4. So I have 12 left. And so I'm going to start giving those as lone pairs to the outer atoms. So I give that oxygen 6. Now it has a full valence shell. And give that one 6. So there goes all of our valence electrons. Now I know you're looking at that and saying carbon's not happy. You're right. We'll get to that in our next step. Now let's look at the ammonium ion. And we said that it has 8 valence electrons. So this was our kind of skeleton from the previous page. And the first thing I'm going to do is attach all the outer atoms to the central atom with a single bond. And now, if you look at that, I put all 8 valence electrons down. I'm out. I can't put any lone pairs in. I'm not supposed to because I'm out of electrons. And that kind of is almost like a nearly complete structure. We'll finish it up on the next page, but that's almost complete for um, ammonium. Now let's look at methanol. Methanol had 14 valence electrons. So we said this was our skeleton. And I'm going to put single bonds for each to each atom. And notice that takes care of 1, 2, 3, 4, 5, 10 valence electrons. I got 4 left. So I'm going to take those 4 and give them as lone pairs to the more electronegative atom, which is oxygen. And now oxygen is happy. And in fact, if you look at all of the atoms, they all have a filled valence shell. So for this problem, we've actually completed the Lewis structure for methanol. Sometimes that happens that way. Great, then we don't have any other steps to do. But we'll verify this on our next step. Okay, so with nitrate, we said nitrate has 24 valence electrons. So our skeleton had the atoms arranged like this. So I'm going to put a single bond to each of them. So that takes care of 6. I have 18 left. So with those 18, I'm going to put lone pairs on the more electronegative atoms, which are oxygen, the oxygens. So I'm going to give this one 6. Now it has a full valence shell. I'm going to give this one 6. It has a full valence shell. And then this one 6. So there's all 18 of them. And now I'm done. Well, I'm not done with the problem, but I can't put any more on there. Okay, so let's look at sulfuric acid, which we said had 32 valence electrons. and we put sulfur in the middle, the oxygens around, and then we gave these guys a hydrogen. So let's put single bonds to the atoms. And I've used up 1, 2, 3, 4, 5, 6, 12 electrons in bonds. So that is 20 left. And now I'm going to start putting those lone pairs around the more electronegative atom, which is oxygen. So I'm going to make this one have a full octet, and this one as well. So that's 12. I got 8 more. Well, I can put 2, 4 here, and 4 here. And that's the last remaining valence electrons. And then finally, acetate. And I'm going to do both versions that I showed you on the previous page, the right one and the wrong one. Um, the right one had our atoms like this, where the oxygens were bonded to the carbon, not to each other. Now that takes away 10 electrons. I got 14 more to put down. 1, 2, 3. Actually, no, sorry, miscounted. 12 electrons. And I'm going to put those as lone pairs on the more electronegative atom. Now let's do this with the one that I said was wrong. So I'm going to put a single bond to everything. So again, that's 1, 2, 3, 4. That's 12 bonding electrons. I have 12 more left, so I'm going to make this oxygen happy. That's 6. Make this oxygen happy. I've put down a total of 10. And then I have 2 more, and I'm going to put that carbon there. I'm out of electrons. I know you're looking at that saying, well, wait a second, that carbon, doesn't have a full octet yet. That's okay. We've out of electrons. I cannot add any more. All right, finally, in our last step is if something doesn't have a full octet, we're going to use double bonds and triple bonds if necessary. It's not always necessary. So how do we do this? Number one, use lone pairs to make double and triple bonds. Keeping in mind that carbon, nitrogen, oxygen, fluorine can't have more than 8 valence electrons around it. Period 3 and below is okay, but not period 2. Secondly, we want to try to minimize or make the formal charge as low as possible. And when I say low, I mean closest to 0. If an atom or if there is a negative charge on the compound, maybe like a polyatomic ion, you want to make sure you put it on the most electronegative atom. And then kind of the third thing you'll want to do is ask yourself, did I make any arbitrary decisions? What I mean by that is you had the choice to put a double bond between a carbon and one oxygen, or you could have put it between a carbon and another oxygen and gotten the same thing. That means you have resonance structures. Resonance exists. And we'll deal with that in some of our examples. All right, so let's put all of this together. Start with our CO2. So from the previous page, this is what we were left with. If you want to go back on your notes and fill out on step 3, that's fine. I'm just redrawing it here. Now the oxygens have a full octet, but the carbon doesn't. So I'm going to use a lone pair from this oxygen and share it with the carbon. Okay, that gets me to 6 around carbon. If I take another lone pair here, I'm going to share it with that with the same carbon. And now that'll put 8 around it. So my structure here looks like this. Now carbon is happy, it's got 8 valence electrons around it, and each oxygen still has 8 valence electrons around it. Now I encourage you to do this, but I'm not going to calculate it here. All the formal charges equal 0. The formal charges on the oxygens and the carbon equal 0. I encourage you go through, calculate it. Put the video on pause. Go do that real quick. All right, so since you've done that, I want to kind of highlight, well, what if I decided to do this? What if the oxygen on the left decided to share 2 lone pairs, and the one on the right decided not to share any other lone pairs? Well, we would have gotten a formal charge of +1 for this oxygen and a formal charge of -1 for this oxygen. And again, the goal of a proper Lewis structure is to minimize the formal charge. So this would not be a correct Lewis structure. This is the one that we would want to show. Now with ammonium, we were pretty much done. Only thing we just had to include, I didn't include it on the last step, but we're just going to include the formal charge. And once you calculate that for nitrogen and hydrogen, you'll see the formal charge is +1 on the nitrogen. Not only that, nitrogen has a full octet around it. Hydrogen's happy with 2. This is one of those cases where we cannot change the formal charge anymore, or at all. We can't change it at all because that ammonium ion has a +1 charge. That +1 charge has to go somewhere. So there isn't any getting rid of that formal charge. Now let's look at nitrate. So this was our result from the previous step. Now the nitrogen is not doesn't have a full octet. All the oxygens do, but the nitrogen doesn't. So according to the statement above, I'm going to use a lone pair on an oxygen to make a double bond with the nitrogen. So I'm going to take a lone pair here and move it down to make a double bond. Oh, wait a second. Why did I do that oxygen? I don't know. I just kind of picked it. Could I have picked this one and done the same thing? Absolutely. But why didn't I pick the other one? Because I could do the exact same thing over there. So I could have I arbitrarily picked one oxygen to make a double bond with that nitrogen. So what does that mean? That means nitrate exists as a series of resonance structures. So we're going to draw all 3 resonance structures where we moved a lone pair from a different oxygen. So that means we'll have one resonance form where this oxygen has a double bond. We'll have a resonance form where this oxygen has the double bond. And then finally, we'll have a resonance form where the left oxygen has a double bond, depending on which we arbitrarily picked to form the double bond with the nitrogen. Now, what we're going to do is see if either of these are these all equally good, or is one better than the other? Well, if we look at all three of them, all three have atoms with a full octet. Okay, so that's good. The other thing we have to decide is what are the formal charges? Now, I encourage you, pause the video and calculate the formal charges of the nitrogens and oxygens. So I'll give you a second to do that. Okay, so now that you've done that, you would have found that these oxygens here would have a formal charge of -1, and the nitrogen would be +1. The one with the double bond, the oxygen with the double bond, would have a formal charge of 0. And you would have found the same thing over here for those oxygens and for the nitrogen. And then you would have seen that for here, for those oxygens, for that nitrogen. So not only do all three have a full octet, all three structures have atoms with full octets, all three have the same formal charge on the same atoms. So what that basically means is all three resonance forms are equally good. Now, there is no way that we can minimize the formal charge. You look at that and say, well, geez, there's like 3 formal charges there. Like, is there a way to fix that? I mean, what if I made a double bond here, like right there? What if I did that? What would that look like? Can anybody look at that and tell me, or I guess tell yourself, why that is not good at all? This nitrogen exceeds our octet rule. It's got 10 electrons around it. Not good at all. So we're kind of stuck with those 3 formal charges. Now, here's the last thing I want you to do. I want you to look at any one of those resonance forms, and I want you to calculate the total charge. So I'll just pick the one on the end here. I have a -2 total and a +1. What does that equal? -1. What's the charge of nitrate? I'm sorry, nitrate? -1. Formal charge should add up to equal the overall charge. All right, let's look at methanol. And on the previous page, like we were pretty much done with methanol. What we're going to do is just kind of double check and make sure that all the formal charges are as low as possible. So again, pause the video, go calculate the formal charge for all the atoms. Once you've done that, you'd see that the formal charges for all the atoms is 0. So we were pretty much done with methanol on the last page. Now let's look at sulfuric acid. So at the end of the last page, we had this as our preliminary structure. Now, what I want you to do is, again, pause the video, and if we were to leave sulfuric acid like this, what would the formal charges of all the atoms be? So if I were to leave sulfuric acid like this, This oxygen would be -1. This one would be -1. And sulfur would be +2. Can I do anything to fix that? Because that's a lot of charges there. So let's take a look at sulfur. Is sulfur a second period element? Sulfur's on the third period. And so those elements can exceed the octet if it helps get rid of formal charges. So notice what happens here. If I give a lone pair, or if I share another lone pair, or share a lone pair with sulfur, and I share one from this oxygen with sulfur, it now becomes this. Now that sulfur does have more than 8 electrons on it. That's okay. Third period and below can accommodate more than 8 electrons. And what do you notice about this structure now? The formal charge of all atoms is 0. So if that central atom is third period or below, we can exceed the octet rule if that helps us get rid or lower formal charges. Now, finally, let's look at the acetate ion. So we had two we were going to take a look at. The right one, which we left off on the last page looking like this. And let's just start there. I'll put the wrong one down here. So if we look at the first one, notice this carbon here is not happy. Doesn't have a full octet around it. So I can fix that by taking a lone pair from one of the outer atoms and making a double bond. So I'm going to take a lone pair, make it a double bond. Now, why did I pick that one? I don't know. Seems kind of arbitrary, which it was. I could have picked a lone pair from this oxygen and moved it down there. So one or the other. So what does that tell you if you make an arbitrary decision to move lone pairs to make those multiple bonds? You probably have resonance forms. So let's draw one resonance form where the double bond is here. And let's draw a resonance form where the double bond is there. Now, if I look at those two, all of them have a full octet. So all atoms have a full octet. Now, what about formal charge? Is there one that has more or less formal charges than the other? So again, pause the video, do some practicing, calculate the formal charge of all the atoms. So when you've done that, you see that this oxygen here has a formal charge of -1. That one over there on the second resonance structure has a charge of -1. So same formal charges. So what does that mean? Both are equally good. Now you might be thinking, well, what happens if I come up against this on on homework or assessment? What do I do? You show the resonance forms. So you'd show all of them, 2 or 3 or however many there are. Now let's go to the wrong answer here and kind of explain now why we're saying this is wrong. So if we look at this, all the atoms have a full octet except the carbon. So what I can do is use a lone pair to make a double bond. And what does that look like? And you say, okay, well, I mean, all the atoms still have a full octet now, or all the atoms now have a full octet. So what's so bad about that? Calculate the formal charges. Again, pause the video, do that for the atoms. When you do that, you'll find that this carbon has a formal charge of -1. This oxygen has a formal charge of +1, and this one has a formal charge of -1. That's too many formal charges, especially when the other option has one formal charge. So that's why this would be an incorrect uh, Lewis structure. Now we just I have one more thing to go over about Lewis structures, kind of some of the exceptions or some things to watch out for. But again, I want to emphasize the only way that you're going to get good at this is to practice it. And as I said before, one of the great ways you can get practice is draw the Lewis structures of your polyatomic ions. I will say don't do the ones that have metals in them. So those are the ones that had chromium. So don't do those or manganese. Those get really, really weird. Just do the ones that have non-metals only in them. All right, and then finally, just I want to leave you with a few more things that you might see. Um, it's kind of rare, but we might talk about it. There are some chemical species that have an odd number of electrons. So when you add up all your valence electrons, the answer might be odd. Notice all the examples we did, all the number of valence electrons were even or added up to an even result. And if there's an odd result, this leads to an unpaired electron, which in chemistry we call that a free radical. They're very, very, very reactive. We'll talk a lot more about them in general. I'm sorry, in organic chemistry. Um, so they're very reactive. They don't typically exist for a very long time because they're so reactive, because they just need to pair up that electron. So an example of this is the compound nitrogen monoxide. That's not the word no, that's nitrogen bonded to oxygen. And if you were to add up the number of valence electrons, it's 11. And so the only valid structure, Lewis structure you can get from that looks like this, where that nitrogen has an unpaired electron. And nitrogen monoxide is very reactive because it has that unpaired electron. Another kind of weird exception you'll see periodically are incomplete octets. These are where atoms don't want to, and I put that in quotes because there really isn't a desire, but they don't want the full 8 electrons. Like, for example, the element beryllium. Beryllium only has 4 valence electrons. So you'll see it quite often, like, for example, BeH2. When you draw the Lewis structure for it, it looks like that. Formal charge is 0. Some other ones that kind of do this are boron and aluminum. It is quite common to see them with only six valence electrons. So an example of this is the compound BH3. If you were to draw the Lewis structure for it, so count up all your valence electrons, you would get this as a Lewis structure. One mole charge is 0. Or aluminum, the compound aluminum trichloride. Again, count up all your valence electrons, and you'll see that you don't have enough to put an octet around aluminum. So it's okay for aluminum to have only six valence electrons around it. Again, this compound has a formal charge of 0. So I highly recommend, again, please practice over and over again. If you don't master Lewis structures, it's gonna haunt you as soon as our next set of lectures because you have to be able to draw a proper Lewis structure in order to determine the shape of the molecule. Now, why do we care about shapes? We care about the shape of the molecule because it dictates its properties and reactivity. And so if chemistry is about the study of molecules changing, its reactivity, the study of its properties, like if you can't draw a Lewis structure correctly, how are you going to be able to predict what its shape is and how that element or compound will react? So again, I emphasize, please master this concept of drawing proper Lewis structures.